So, welcome back. We are searching for my arrows, and the error was just that I do many mistakes, that I did many mistakes. Since if you are data crunching, making data crunching, then you have to be careful that the formulas are right. Actually, I'm always talking about using artificial intelligence, and yesterday evening I did some calculations using ChatGPT, taking derivatives, setting them to zero, all nonlinear, quite complicated. So doing it by hand will take a while, and I was quite fascinating because almost everything was reasonable. And then at once I saw there was there I had to calculate the zeros of a cubic equation, so x to the power of 3 plus 5x minus 2 or something like this. And then the guy has done it just wrong. It came out just the wrong number. And this is maybe similar to this here, because then I just went through the results and I just saw, well, the result is not reasonable. It cannot be true. Well, I cannot do it in my head, but I know that the that the outcome is wrong. And if I see here an R of 0.003, and we have talked about this before, where are my data points? We said maybe 0.7, maybe 0.8. Yeah, and therefore there has to be something wrong. Well, and the starting point, doing something wrong, is going very fast through it. This number is still right, so 7 times 472, because we need n times the sum. And then I just copied this to the right, and of course everything is shifting to the right. And if we click in this here, then it is not 7 times the sum, but it is 22 times the sum. And it becomes worse because this number is then 145 times the sum, and then of course everything has to be wrong. So then let's correct this, and hopefully then it works. So, and then here we need the sum of x and sum times y. This is, I think, okay. Yep. Great. Actually, I'm starting from 1 to 6. Yeah, of course. This is also wrong. So I have to change this. Um, so you are right. This is wrong. Fortunately, it doesn't matter because this n in the end is canceling out because you are multiplying everything with this. But actually, you are totally right. It's only 6 data points. Great. Thank you very much. Yeah. So we need, oops, where are we? My formula. Um, Sum x times sum y is 24 times 94. This is okay. I think this is also wrong. X squared, this is the sum of x squared, and then I took the square of the sum of x squared. But within this bracket here, I have the square of the sum of x. So again, something wrong. So this has to be 21 squared, and this also, this is the sum of the square squared, and again only the sum squared. 94 squared, and now you see that this r and this r coincide, and we are through everything. Let's calculate also r squared. And the formula for this coefficient of determination in Germany means Bestimmtheitsmaß. And you see here first y values and then x values. What do you think what happens if I'm reading in at first the x values and then the y values? If you look into the slides and the formula, if I'm pressing now enter, will it be another number or the same? Because if I see the formula within Excel, then he says to me that at first I should read in y values and then x. If you just have a look into your slides, you don't see it here. If you look into the formula for the coefficient of correlation. Or let me go here. If you look at this formula, well, if you look at it in the first part here, if I interchange x and y, nothing happens. It's the same number. Interchanging the sums, also a times b is b times a. This you have learned in primary school. And down here, if I calculated first the variance of y and then the variance of x, of course, it also doesn't matter. So this formula is totally symmetric within x and y. And therefore, hopefully, enter means interchanging x and y. Nothing changes. So let's maybe put this here also, totally symmetric in x, y. And there you have to be a little bit careful with the linear regression, because then you could think, and this is maybe a little bit surprisingly, that if you look at this, that you would say, well, it doesn't change anything if I'm interchanging the axes. The data set is still the same. But there actually it is not true if you are fitting y equals a plus bx, calculating then A and B, or if you are interchanging the relation and you say x is A tilde plus B tilde, so principally some other coefficients, and then actually you can show that these numbers are not the same if you are fitting x is A plus B y or the other way around. So the linear regression is not symmetrically due to an interchange of the variables. So be careful. Interchanging within the linear regression x and y would give you another result. And actually, but this we will not do here. In the term papers last semester, I posed this question. Then you can show that the product of the two slopes is just, again, the coefficient of determination. Okay. Yeah. But now, if we have done all this stuff, we can calculate everything for the other series, since it has the same format. Oops. So then here we are. So let's see how our estimates were. We had 0.985 and 0.971. Up, where are we? Here. So this was 0.985 and 0.971. And in the other case, I think we were a little bit better, minus 0.47, minus 0.47 and 0.27. No, 0.22. So maybe we could have had here, I don't know, that it is that close maybe, but here, since we have seen when we take the square of the correlation coefficient and we are really in the neighborhood of 0, there it could be a hint that the number is a little bit larger than this at first estimated minus 0.2. But if you are doing more and more quantitative stuff like this, then you will develop a feeling by just looking at the data where could be the coefficient of determination. Okay, I think about this we have already talked in detail, especially remember this nice interpretation that the number of the coefficient of determination can be interpreted somehow in this percentage is explained via my linear model, and about this picture. I also had talked already that at first, relative to the mean, this is, so to speak, the first shot, creating just a horizontal line through my data set and then turning now here with a falling line with the data set of the anti-proportional dependence between the two variables, that then I somehow get a line which is somehow a little bit closer to my data, qualitatively spoken. And yeah, then this can be in general be shown that R squared can be also calculated with the linear regression. Well, maybe I can post this as an exercise, this question, why this is true. Because then you also have to recalculate with the summation signs and so on. Okay, but then I think this I now can copy and we can redo our calculation just with the linear regression, and then we see the dependence up between. Ja, jetzt komme ich hier wieder nicht runter. Doch. Between the linear regression and the correlation analysis. So this was then y hat, and this was y hat minus y bar squared up and y minus y squared. So we need the arithmetic mean of the y values, and then equals value minus mean. Now I directly fix it and squared. Then we need the theoretical values. Of course, this we have done last week, but we also know that we directly can do the linear regression with the formulas. Now it is important that you do not interchange x and y, because then you get other values. So y values and x values and our slope, German Steigung, y and x. Oh, this was again my example, which I had already done. Now we are calculating the theoretical values. So this would be then a fixed plus b times x. And this we can move downwards. Up. There's something wrong. Let's click inside. So 12 times 9 plus, no, it's okay. Okay, these are almost the same formulas, and therefore I copy this formula, paste it, and now I read in the wrong column, and it is not P, but it is Q. What do we need? We need the sums. And then this is, so to speak, the explained dispersion, so relative to our turned linear line, and this is the overall dispersion. So 482 over 572 should be then our R squared. And hopefully this is then true. So let's do it again. This with the implemented formula, and now I've done it in the right way. Okay, yeah, why I am investing so much time, although we directly have all the formulas implemented in every statistical software package. In my opinion, it is a useful thing if you have done it once somehow by hand, or just, yeah, typing all these single steps within Excel, because then you, in my opinion, get a feeling about what you are doing there. I really often said in colloquia, in bachelor theses, and then asking the students, what have you done in your evaluation of your surveys and so on, and what does it mean? And yeah, this is the outcome of my statistical program. And what does it mean? We don't know. And a little bit more than 50 years ago, in 2008, we had the outbreak worldwide of the financial crisis, and still, I think one of the main reasons, or one of the reasons, maybe not the main, or I can say the main, is that the guys within the financial towers in Frankfurt, in London, in New York City, they feed it just in the data, in their Excel sheets or in their programs, pressing enter. Wow, this is triple A. This I can sell for very much money. And then they were quite surprised that within 3 months, I think it was, this was PNB Paribas. This is, I think, the largest or second largest bank in France. And in 2007, in summer 2007, they had a balance sheet of, I think, roughly, in this time, roughly 1 billion or 1.5 billion euros. And then they announced, well, we have here an investment portfolio of more than 100 billion, so trillion, we are here in English, so balance sheet trillion euros, and we have a portfolio of investments of more than 100 billion euros, so roughly 10 to 20% of their overall balance sheet. And they just said, well, we have to see. We don't know what is the value of this. we have to recalculate. Maybe in other lectures you have heard that due to the regulation you have these risk adjusted values. So this is this market-based Anglo-Saxon concept to always look what are the prices within the last 3 months, within the last 6 months. So you are not valuing your financial assets. Well, what have I paid for that? But how has the price developed? And yeah, then they just said, we don't know what is the reasonable price of this. And unfortunately, the outcome was not AAA anymore, but C, investment grade. So full depreciation of 95%. So this is not very mathematically spoken, but I say you have to have some feeling what is the value and not just feeding in the data, pressing enter and say, well, this is what my model says. You have to value, is it reasonable? And I think this will become much more important because we will use artificial intelligence. This makes us much, much faster. And so it is your task that you can value the output of the artificial intelligence. Is this reasonable, what I find there? Okay, so we are done now. And this we have already set, interpretations. And now we come to the interesting part. But now I won't go through this step by step because now the formulas become more complicated and more complicated and more complicated. But of course, in general, we do not have only one independent variable explaining the other one, but in general, we have many variables explaining many other variables. And then we can apply still the same concept, but then of course it is called multiple linear regression. That thing we had in our example said, well, our sales volume depends on the number of visits, but it can also depend on your marketing budget, in which kind of branch are you, how many stores do you have, and so on and so on and so on. And of course, all this you can also feed in, and then you make again some assumption that you have just any function, how these variables x1, x2, xk. So the first one would be the number of visits, the second one your volume of your marketing budget, one the number of your people, and so on. And yeah, then again, maybe the easiest way how your function could look like is then again, well, it is just a multiple linear function. And then we do not have a plus bx, but we have again one constant and then just a factor many betas in front of our other variables. Well, and we apply again the same concept as before. In general, our model will not fit our data with 100%. So if we would know all our betas feeding in our X values of our data set, then again, we will get some outcome, but this will not fit the y values of our data set. So again, we have some error for every data point. But now I cannot draw a diagram anymore or in 3 dimensions maybe, but the 4th dimension will be quite hard to do this. But if you have the 2-dimensional concept in your head, then I think you know what I mean. Okay, yeah. And now I think class 11 or 12 in school, then we can write this here. Of course, this has to be done for y1, y2, y3, and so on, downward. And this then can be rewritten in matrix form so that we have a very compact setting for this. And we have, of course, our data points, the x data points. Y values of the data points. So this is then a vector, and therefore I put the arrow above our letter. I think this you have done in school too. This is not quite often done in the economics literature. I don't know why, because this is very intuitively, and you are doing this in school, in physics, in mathematics. You are generally putting, if you have only one column, then we call this a vector, and showing that this variable is a vector in mathematics, in physics, and so we put an arrow above this. Please be not surprised if you do not find this in in economics literature. Yeah, then of course we have also a vector of our betas, or all betas form also a vector. And for every y1, y2, we have different arrows. So we have n lines. So our arrows are forming also a vector. And then unfortunately, this is a little bit more complicated because X is then a matrix, and we are adding this column with 1 in front, because why? Well, we have this constant of beta null, beta 0 in front, which we do not multiply with any x. So if you maybe at home go a little bit slower through this representation, then just write yourself down this thing here. So y1 equals beta 0 plus beta 1 x 10 plus beta 1 x 11 and so on, and all this. And if you remember, let's say, I think in this way you have done it in school. Do you remember how you are multiplying a matrix with a vector? Everything is coming back. Hmm? So you are starting horizontally, and then you are turning 90 degrees and multiply every point with each other. This is the so-called scalar product. So if you remember, I think this you remember in school. What are you doing? Multiplying two vectors. How are you doing this? Yep, diagonal. No. No, I think you are remembering 3 dimensions, and this is then the so-called cross product. This works only in 3 dimensions. So you have also this one here, but then not a dot, but a cross, y1, y2, y3, and then you're starting to multiply this, this, and then in the end, this and this. This is just x1, x2, y1 plus x2, y2. And multiplying a matrix with a vector means you're taking this also as a vector, as your starting vector, multiplying with this vector. So this is then a11 plus, x1 plus a12 x2 and a21 x1 plus a22 x2. So a matrix times a vector is a vector. I would recommend that maybe you have a nice little thing what you reread this weekend. Okay, but so you have to believe that I can represent it like this. Yeah, and what we want to do now is, again, we want to minimize the sum of all squared errors. So minimize epsilon squared. And this is just epsilon vector times epsilon. So it is epsilon 1 squared plus epsilon 2 squared and so on. This is the same as in the two-dimensional case. This we want to minimize, and please do not hate me, because now we have to do a little matrix manipulation. And it is a pity, maybe the difficult thing with matrix multiplication. So a matrix in general we write as a bold letter. So unfortunately, for two matrices A and B, we have A times B is in general, it can be, but in general, it is not the same as B times A in general. So by accident, it can be the same, but in general, it is not the same. So what you know that 3 times 4 is 4 times 3, this is not true anymore. And if we then multiply these constructed things here, and especially what we then have to do is we want to know, well, how does this sum of all errors looks like independence of our data. So how does it look like independence of x and y? And therefore, we also using these matrices and vectors, we are doing the same as in the two-dimensional case. This can of course be rewritten, and plus and minus, there you do not have any problems with vectors and matrices. So this you can do, you can use your rules you know from your usual numbers. So epsilon vector is y vector minus x times beta and bold x. So, and this then means if we square this, we have to square this one. And then, oops, this hopefully you also have to have learned in school that if you multiply two matrices with each other, that yeah, in general, if you when you first introduce it, you use it like this, but then if you say a times b, or here y minus x beta squared, that you write this then, because this is again a vector. Yeah, so epsilon for its own is a vector. So this is of course also a vector. And now I want to explain what this t means, or does anybody know if we write on a vector or at a matrix a t, what does it mean? This is the operation. What means this t? So if we have a is 1, 2, 4, 6 maybe. This is our matrix. Was it then a t? Anybody? No. So this t means transposed. So we are just interchanging columns and lines. So AT is on the diagonal, of course, nothing changes. We have the 1 and the 6, but the 2 and the 4 are changing places. So 4 and 2. And a t, so if we have then a t at a vector, so if epsilon is epsilon 1, epsilon 2, epsilon 3, then epsilon t means also interchanging columns and lines. Well, we have here only a column. So this just means that this vector translates into a row vector. So this means then this looks like epsilon 1, epsilon 2, epsilon 3. And the idea behind this is if you then write epsilon 1, epsilon 2, epsilon 3 times your column vector, epsilon 1, epsilon 2, epsilon 3, that you then can also apply on the vector multiplication your rules from your general matrix multiplication. Because remember here, where did I had it? Oops, where did I do it? Was it here? I said we take this line, this row, and then turning 90 degrees, multiplying with this one. So this then here means we are taking this row, turning 90 degrees and multiplying with this in every for every number. So this is then epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared. Yeah. Okay, but we have already 45 minutes. So if you have time, then just go through this, and you also have to keep in mind one can in general show that A times B, two matrices, and the product transposed is not A transposed times B transposed, but it is B transposed times A transposed. This is a rule which can be generally shown. And yeah, if you know this rule and go through all these calculations I've done here, then you will see that hopefully I have not an error in my slides. Okay, so then doing these calculations here, we have then this representation, and well, what we want to do is this should still be minimized. And how should it be minimized? Well, we want to change all our betas in such a way that this sum of all squared errors is the lowest possible numbers. Is the lowest possible number. So if we, let's say, have here, as in this case, three variables, then of course we also have three betas, and then we have to calculate every partial derivative with respect to every beta and setting this to 0. And this, I don't know, this should have been also done in school, that if you have in general an n-dimensional function, this is then called the general derivative with respect to every variable. This is the so-called gradient of this function. This is nothing else than writing it in a very compact manner. This just means please take the derivatives with respect to all variables. Nothing more and nothing less. And this I've done here at the next slide. This can then be written as that I'm not writing the derivative with respect to some variable, but with respect to an vector. This representation here just means please take all derivatives with respect to all betas. And then In general, one can show that although we have here vectors and we are taking the derivative with respect to a vector, that we more or less can do this or can treat this in the same way as we would have just only one variable. Yeah. So this is once this is generally shown in mathematics, and then you can do your calculations like you know it from school. So, and this means here we have a linear exponent 1. So this then just vanishes. And here, although the beta is at first at front of the matrix and then in the behind this matrix, we intuitively, I think, see that this is somehow something like beta squared, or this is a product. Well, you cannot fit them together and writing their beta squared, because this would be because you are not allowed to interchange your x's and betas. But in general, the idea is that you are multiplying 2 times with the beta, and this is then again something like beta squared. And beta squared with respect to beta, the derivative is 2 times beta. So from this, we have this 2 again, and we have this beta left. And then we have a quite fine situation. All this has to be 0. Actually, this is not only a 0, this is unfortunately also a 0 vector. So this is 0, 0, n times. It's just a compact way how to write it. And plus and minus, there we have no problem. So putting this on the other side. And then we are solving for the vector. And here again, we have to be a little bit careful. If you have numbers, then you just would divide by this part. But since this is a matrix, you have to do it. A division has to be done a little bit in another way. You have to multiply both sides with the inverse of this matrix. So if you have an A and the inverse 8 to the power of minus 1 is defined that 8 times the inverse of A is just I write it like this, the identity matrix. So this is then a diagonal matrix with only ones in the diagonal and zeros in all other places. So maybe you can compare this if we would write, let's say 3 is 4 times x, and we will want to solve this with x, then of course, you know, well, I'm just dividing by 4. Or you can also say I multiply from the left side with 4 to the power of minus 1. Yeah. So this would be then 4 to the power of minus 1 times 3 is just x. And if you have only numbers, of course, then it's just 3 by 4, of course. But this is, of course, much more complicated if you have matrices. I'm sorry for this, but this is how it is. Yeah, but then all this is known. These are all our X numbers, and these are all our Y numbers. Well, since this in general is a quite high dimensional matrix, then unfortunately calculating this inverse is quite a hard task. And until we have developed computers, this was very hard to do by hand. And in general, well, there is an algorithm that you can calculate this deterministically, but this takes very, very long and many, many steps. And therefore, this is still done via approximation methods. But we will just assume that it is probably done. This we will not do here. But really, my question, just to invert a 4x4 matrix or something like this by hand, have you done this in school? This is the so-called Gaussian algorithm. I think in general this should be done in class 9 or 10 when you in the first time are introducing a matrix. Well, of course, since we have now our software package, you can ask, do I really have to write 3 pages full until I'm ending up with the inverse of my matrix of a 4x4, because it takes really a time. But on the other hand, to see it just once and then know what happens in behind, feeding in the data and pressing enter, this is still, I think, a good thing. Okay, but now we just assume that we have done the inversion of this matrix, and then we are just calculating everything and we obtain our betas. And if we then have our betas, we can again just directly calculate our coefficient of determination, because now, since we have our betas, we can calculate our theoretical y values. And with this, again, we are calculating the variance, so the explained variance, divided this by the overall variance, and this is still the definition of our R squared. So here we have actually the same as in the two-dimensional case. And yeah, now I won't go through the example I have here with you due to the time, but in general I formed just using our starting example, and now still we have our number of visits. Then I just assumed that in every year we have some differing marketing budgets, and we also would assume in some region, maybe you have a region or not, so I have here now not in time, but I have 1, 2, 3, 4, 5, 6, 7, 8 regions. Let's say Wilhelmshaven, Friesland, Ammerland, and so on. I have an overall budget for the marketing in my different regions. And branch means there is one branch located or not. So in Wilhelmshaven, if A is Wilhelmshaven, then I assume here I have a store, and the next one is maybe Sande, and there I don't have a store. And this is then a so-called dummy variable, because at first one could say, well, how should I quantize this? Having something and having not something. And this here just means having a store in the region means a 1, and having no store means just a 0. And this is called then a dummy variable. So, and this would be then my y, and this my x1, x2, and x3. With these numbers, maybe this you can do at home because it's not that much, that you then just try to write it down in this way. Because here you just find your x values, and here you just find your y values. So that you have a feeling, how does it look like? What is now my matrix X? Yeah, and then I have these X matrix, where this X matrix have my X values added, this first column with all ones, and then I have to calculate X times the transpose of X, and then calculating the inverse of this. Yeah, so what we need is just to obtain a result for the inverse matrix, and then multiplying this inverse matrix with the transpose of X, and then in the end multiplying this with the vector of our Y values. Let's say calculate X xt inverse times xt times Y vector using AI as a homework. Yeah, and I give you the result, because if we calculate this, then we obtain, of course, a beta 0, 1, 2, and 3. So the result is then, let me see, beta 0 is 742, beta 1 is 0.43, beta 2 is 0.46, and beta 3, this is nice, is minus 3.00. And we can also calculate then an R squared, and this is 0.72. Of course, this can also be done in Excel. You can download an additional software package where you have a quite nicer menu where you can just click on your data, getting out these numbers, or if you look at Google and just ask how to do a multiple linear regression within Excel, then you will find this too. Okay, this then we do not have to do. This would be now the same calculation as we have already done this in for the two-dimensional case. This is for the calculation of r squared. So 20 minutes left. Yeah, then we will now start with a maybe interesting part of statistics. Because what we have done right now only, and there you really have to be careful and please keep this in mind, because this is very, very often mixed up even by clever guys. Well, if you have this regression, and here we have this beta 1, this is the beta value in front of x1. Well, the interpretation is still the same. If I increase my number of visits by 1, keeping everything else constant, my cells volume will increase due to my data by 0.43. And I have an idea, well, I have a r squared of 0.72. This means 72% of my data is explained via my linear regression. But still, this is only a descriptive calculation which we have done. Still, you cannot argue for any causality. And now maybe comes the really interesting part of statistics. The guys who have participated last term in the exam, there you have done this. Well, I can calculate given a data set, I can calculate the arithmetic mean, but maybe a survey, I ask 1,000 people out of all possible consumers in Wilhelmshaven, 80,000 inhabitants, means between 20 and 60, I have roughly 40,000 possible adult consumers, or we can also take the pensioners, so let's say 55,000, and I'm asking 1,000 of these guys, how much money you want to spend for a special product, and the average answer is 500 euros. Then you want to have an idea how good is this answer asked 1,000 people out of an overall set of 55,000 people. Can I take this average answer and then assume, well, the possible income is then 55,000 times 500? How, qualitatively spoken, how good is my estimate? And this is the hypothesis testing. And now we also want to ask for our linear regression, how good is my fit? And not only relying on this r squared. So please keep this in mind. Until now, it's only descriptive. And this is very, very often mixed up, even by clever guys. They just said, well, I have here calculated my averages, or I have done my regression, and now I assume this is how the world is functioning. Then we are in the financial crisis again. So this means we have still now no idea of causality. What is the right model behind it? And please do not mix up correlation, so an r squared in the neighborhood of 1, with causality. An r squared of 0.99 still does not mean that you are using the right model. You have only a very high correlation. Well, some old professor in investing in financial markets, he said, well, an overall very stable correlation over 20 years. This I take. This is enough for me to buy the stock again in the future. But you still do not have an explanation that this stock will increase in price also in the next time. Yeah. Because in general, we do not have the full data set. Take my example, 55,000 consumers in Wilhelmshaven, and you are asking 1,000 guys. So, and now we want to draw a reasonable conclusion having some survey data. How can I rely or how can I overtake these outcome of my data set onto the whole sample? And now comes a really important thing. All what we are doing now is that we are assuming some special things about these error terms. And the maybe most important assumption is that our error terms are a random variable too. So they are fluctuating statistically. And the first personal topics in the term papers then, heteroskedasticity, multicollinearity, autocorrelation, and so on, they are all about the problems that the main assumption which we make now, that it is following a normal distribution and all error terms are independent from each other, that this is a really strong assumption which we do not find totally fulfilled in practice. But this is a random variable. And this is also quite often forgotten. Well, if you are doing only descriptive statistics and within a survey, sometimes you have outliers. You say, wow, this answer is really not reasonable. What has this guy done? And then you take these outliers out. You're arguing, well, this is an outlier and this answer was not reasonable. And from a descriptive standpoint, you can take this data point out of your data set. If you want to do hypothesis testing, so a conclusion, how good is my survey predicting the the parameters of my whole sample, then you cannot. You are not allowed to take these evil data points out because, again, you have the assumption of a normal distribution. Well, even here and here, the normal distribution say, well, it is not very probable, but it is possible. And once I was at a workshop and there was some nice lady, and then he said, well, here are, I don't know, 10 data points and the answers were not reasonable. I have taken this out. And then after half an hour, she started to present her calculations for the hypothesis testing without these outliers. There was one guy who was asking, well, do you know what you are doing here? This is not a random variable anymore. If you say, well, I'm manipulating my data. Actually, when I wrote my my diploma thesis in physics, there we did when we did the measurement, we did once, yeah, we have to admit an error. We changed our electric field from plus to minus, so we interchanged the field direction. So we had charged particles who should be decelerated, and since we have interchanged the field direction, we had two data points with an acceleration of our particles. Then we had these data points. And unfortunately, these data points didn't fit our theory we wanted to show. And then there was an old professor from Italy, and we were discussing, well, because our other was not that much data, I think about 15 data points, so to speak, on the left, fitting our theory, quite nice. And then these other data points with the acceleration, which didn't fit our our theory. Well, but then he said, we cannot leave out these data points. There's a good argumentation that the whole setup has changed because of this other field direction. But anyway, these data points are there, and then we are not anymore within 1 sigma, so 1 standard deviation in the fluctuation, but 3, and well, the outcome was not very nice anymore. But anyway, that's like it was. Okay. So, and now we come to the strong assumptions on these error terms that we can do this hypothesis testing in general for the multiple linear regression. And your task then in your term papers is to say, well, what happens? What do I have to do if my errors are not independent anymore? Well, this we will still make this assumption that the average of all errors, no, or not the average, the expected value is just 0. And this also a very strong assumption that the variance of every error term is the same. There, I think you can think of that this is a quite strong assumption. Why should they all be have the same variance? And this is then called homoscedasticity. I don't know, is somebody in here who has this topic of heteroscedasticity? Hetero means just they are different. So that hetero oh yeah, then maybe you have already read about this. Skedasticity. This means then variance of epsilon I is a sigma I squared. And in general, sigma I squared is not the same as sigma j squared for j not the same as I. Yeah, then autocorrelation. This means that we have a nice feature for the covariance, that the covariance is just 0. This also do not have to be 0. And of course, this one, all error terms are normally distributed, and especially the assumption of a normal distribution of errors is not very often found in financial data. So in financial data, quite often we have so-called fat tails. And what does it mean? Well, the normal distribution goes very fast in the neighborhood of 0 if you go to the right. And if you have then here a density function which has much more probability mass in these outlier regions, then you have not a normal distribution anymore. So extreme happenings we see in financial data much more often than it would be due to the normal distribution. Something like the financial crisis should happen not that often if such a crisis would be a random variable with a normal distribution. Okay, I think through the next 3 we can go through, and because now what we are doing here is we assuming doing our linear regression. We are estimating these betas because we are assuming that the dependence between our x variables is a linear dependence to our y variable. But of course, we have our finite data set and we have a much larger overall sample. And therefore, these are only estimates. And then we, in general, ask for, so to speak, good criterions. When do we speak about these estimators that they have, that they are fitting a good criterion? And the first one about this, I have already talked when I said we are dividing the variance by n-1 and not by n. This means that this is a so-called unbiased estimator. I think you should show this or in your exercise next week. And this then means, well, this is our data. I can calculate the expected value of our data. And if this estimator is constructed, that I can say that the expected value of my estimator is the true value. Well, I cannot calculate this, but I can show this theoretically. Yeah. That in general, I'm not always 1 unit at the left because of the construction, how I calculate, for example, the arithmetic mean. And for the arithmetic mean, we can show, well, this is an unbiased estimator. If we would divide the variance, the sum of the square distances through n, through the number of our set, then we can show that we are always a little bit too low in order to fit really the true variance. So this is one criterion. The next one is, well, of course, we can think of many different possibilities to calculate an estimator, let's say, for the expected value. And then we can calculate the variance of every estimator, which we have calculated in different ways. And what we then say, well, we call an estimator efficient if out of all possible estimators, we have chosen that estimator who has the smallest variance of all. And I think this is also quite clear why we say this is a good criterion, because in the end, remember, we want to do something so that we can conclude out of my data set, I can conclude something to the whole sample. And if I then would calculate an estimator which has a very high dispersion, then it is not that helpful compared to an estimator where I can say, well, it is always quite close in the neighborhood of the true value. And this we call efficient. And yeah, then a little bit faster from statistical theory, then sometimes it is not that easy to calculate such an unbiased estimator. And then we are also quite happy when we find an estimator where we can say, when we just increase the number of our data set, let's say from 100 data points to 1,000 data points, and if we then can show that our estimator becomes closer and closer and closer to an unbiased one. And this we then called asymptotically unbiased. And yeah, what we then in statistics also have is in school, we always said, well, we have a function f of x, and then we assume, well, it is quite a smooth function. So we have no jumps looking at these functions. Well, if you are throwing a dice or just throwing something into heaven and then it comes down, in statistics, you have something which is randomly fluctuating somehow. And for this, in statistics, we have to develop other convergence concepts. You know from school that you then say f of xn for n to infinity moves then to the true function f of x. Something like this you have maybe done in class 11, 12 or so. Yeah. And this convergence process here in statistics, this is somehow a little bit more complicated. And for this, then we define the so-called consistency. And there you then apply this statistical concept of convergence. And if our estimator is statistically convergent to our true value, then we call this estimator consistent. And the last one from decision theory is sufficiency. And for this, we say we have a sufficient estimator if this estimator uses only the relevant data. And this is especially very needful to come down for the calculation from a really large information set. Because still calculating means time. And think, for example, flipping a coin. Then you can say, well, I have two states, heads or tails. But you can say, If I'm head, then I'm knowing that it is not tail. So, and this directly reduces the relevant information by 1/2. The overall information is the information about the two states. But since I know if I have one state, I know it is not the other state. I need only 50% of the overall information. And if my estimator is then calculated in such a way that it uses only this relevant information, and for example, if you take the binomial distribution, which is just this 50, or is just this 0, 1, two-state experiment, then you are using only this 50% of the information. And then calculating the mean and the variance n times p, and then it is n times p times 1 minus p p for the variance, and p is the probability that you have a 1. This is then a sufficient calculation of your estimate. Okay, now I'm already in the overtime. How should I then go on? Okay, then the next days I will do for you, I will make 2 videos that I'm going through this hypothesis testing. So now we have talked in general what is all about, and here how we are doing then this hypothesis testing. So how good are our estimators for our beta values? And what I'm then also doing is the next topic is inequality metrics. This will be then in 2 weeks, the general talk of other students. Okay, thank you very much for today.